Okay, here we go. So this is a pretty standard proof of our theorem here. And just so we can kind of keep in mind what's going on, now a little function diagram. And we start out with, here's G, here's the image of G, and phi is our homomorphism, and we probably have some different elements. They all map here, and then maybe another set of elements that map here, and another set that maps here, because I don't feel like making this. Ooh, don't clear all the screens. I just want to change the size of my eraser. What are you doing to me? Well, made my eraser too big. Now I had to do more dots. All right, so that's our homomorphism here. And then if we want to think about our isomorphism, which we are calling beta, it would be chunking these out to cosets and thinking of this as one single line instead of a bunch of things going to each other. All right, so very zoomed in, gross picture, but we have nicer ones from earlier. And of course, here is our beautiful theorem connecting all of our stuff. Let's take a look now at our proof. All right, so we had a bunch of sub-goals where we're talking about beta having certain qualities that actually make it an isomorphism. Here's the first piece. We're noting that the kernel of phi is normal in G, which is a theorem that we already talked about being true. Why do we need to note that? And again, pause, think about this for a second. Well, this is important because normality is what was required for G, for kernel phi, this quotient group. For it to actually be a quotient group, right? Remember, if we didn't have normality, we had problems with the operation not working right, we didn't have closure, the structure just falls apart. So we can note that, so that means that we're actually, in fact, working with a quotient group, and that this makes sense to continue onwards. All right, so then our next piece here, just like we talked about before, is that we have to introduce a map that's going to be serve as our isomorphism between the quotient group and the image. And we can see how we're setting this up. Well, we're basically saying that we're going to take a coset. All right, so we have like one of these cosets here. And then we see, well, where does one of the elements go? So we follow a blue line. It ends up over here. And that is where we're going to have our green map. So all the elements in this coset, we're going to say this whole thing together, the subset maps to phi of G. Just kind of like zoom out on our picture. So let's say that this is our element G is right here. Maybe we have H and K or something. Or maybe we have, let's just call this G1 and G2. And we're saying that our coset, and I put my green in here so it's like the picture, this whole thing, the isomorphism map, takes us to wherever phi of G got mapped. All right. So that's our definition, that if this is our G coset, and also note that we're just using capital K for kernel phi, so we don't have to write it over and over again. We have this coset, and we're going to say my isomorphism map is going to move this entire coset to wherever G happened to get mapped, which is exactly what we see going on in this picture here. All right, so we've set it up. Now, as I mentioned before, since we're using a representative element to say what's going on, we have to actually argue that we have something that's well-defined. So our well-defined piece comes right here. And let's take a look at what this argument looks like. And I'll just keep kind of notating here. Well, what does it mean? It's saying I am picking the same coset and I'm giving it two different names. So I'm worried about this coset right here. And I know I could call this coset G1 if I wanted to, the coset made by G1. I could also call it the coset made by G2. I could call it whatever representative element I want it to. And what I need to check is that if I put it through my isomorphism map, and I called it G1, or if I put it through my isomorphism map and I called the same element G2, that they best be arriving at the same place. That this green line is consistent, that it doesn't matter what I name this coset, it goes to the same place. All right, let's take a look at how that plays out in our proof. Well, first thing we do is, we check out where does beta of G1K go? Well, by our definition of beta, it says that I hang out and I see where does G1 go, which is phi of G1. All right. And now there's a little bit of a trick in here, and I'm going to hold off on a second and just kind of draw our attention to the other side, which is what is going on with if I put the G2 through, by definition, that's phi of G2. And our goal is to show that these things are equal, that the stuff went to the same place. How do we do that? Well, we introduce a nice little kind of, I don't know, clever approach in here. And here's the piece that I want you to think about for a second. We're claiming these things are equal, that phi of G is the same thing as phi of G1 times phi of K, where little k is something inside of our kernel. You can see it written right there. Why can I do that? Why are we allowed to just insert this line? Good place for me to pause again, and you can think about this and unpause me when you're ready. Well, why can we do that? Well, because if you're in the kernel, that means we're just operating by the identity. That's the definition of being in the kernel. All right, how do we get from this line to this one? Well, here we go. We are homomorphism, so I'm in good shape. And this is the piece that's like, wait, what? Why is this working? Why can we go from phi of G1K equaling to phi of G2? Well, first, let's see what k this is. This wasn't actually an arbitrary k. This k was picked so that G1K equals G2. Okay. Well, that probably changes our question then to ask, like, why? Why can we find a G1K that's equal to G2? Why does this k exist that allows for this equivalence? Well, what do we know about G1 and G2? They are in the same coset. So G1 is inside of the coset G1K. And since they're both members of the same one, G2 is also inside of G1K. And what is that? Well, it's G1 times various Ks. All right, so if G2 is a member of this coset, because they're in the same coset, that means for one of these things, G2 must equal to a G1 times a K. All right, so it's because they're in the same coset that we can hunt down whatever K it is that would match up the parts being equal. All right, so that's a lot of side work to get us this important piece, but that is what allows us to then make this important claim in the middle here. So if we zoom out, we are well defined, because if I take the same coset and I called it G2 kernel, or if I called it the G1 kernel coset, and I plug them in, I can do a little bit of manipulation and find out that they are going to the same place. The naming doesn't matter, so we are okay on well defined. All right, you can see thus beta does not depend on the choice of coset representatives, and the map is well defined. All right, so after well defined, the next thing we can do is worry about showing that beta is actually a homomorphism. And hopefully we feel pretty comfortable with how this process works in general. But we know that our goal for a homomorphism is that if I pick two arbitrary elements, in this case now we're talking about G1 of K, G1K, and G2K being my arbitrary cosets. All right, so I'm picking two things from my domain, a G1K and a G2K, as elements from my domain. Then I put them through my beta map. My goal is to then arrive at the fact that I could have put them through the map independently and operated them second. Again, we've got some pieces here if we wanted to play it through. Right, this is just how coset operation works. We know now that cosets, we can just operate the representative elements. Then what is happening here? Well, that means that we took the G1, G2 coset, threw it through our beta map. And what does our beta map do? It maps us to where the homomorphism image is. Then we can use our homomorphism property, expand it out, and then unpack, well, phi of G2 is exactly what beta does. Beta sends things to those images, so we're in good shape. All right, so we do have a function, we do have a homomorphism. The last pieces that we have to worry about are, do we have something that is onto and something that is one-to-one? Well, here's our textbook version of writing things in proofs that are apparently so obvious we don't have to say them, and does a very good job at making any of us who didn't immediately see this not feel good about ourselves. But just, keep in mind when things are very clear to an expert mathematician, it does not mean that they have to be immediately clear to people who are just learning, right? We're undergraduates and we're just developing our sense for how to become mathematicians. So that said, I would like to unpack this and not just say clearly, why are they making this claim that clearly beta is onto phi of G? Right? Well, when we're saying onto, that means that if I pick an element, anything I want from my codomain, right? Just to kind of remind us what our map does. It goes from the cosets to the images from the original homomorphism. That I can find something that maps me there. Let me convince myself this is true before I just let this clearly go away. Well, if Y is something that is in the image from our homomorphism, that is our original map, not our beta map, then that means there exists a little g from our domain itself, such that phi of G equals Y. All right. Haven't gotten to the beta yet, but I can. So then beta, that's our map that goes from the cosets to these things. What is the one that gives me little g? Well, it's going to be my little g coset. So that's the thing that hits my image. That's the thing that hits my codomain over here. So I am good, and it wasn't that hard to talk about the onto, but I still wanted to before I just convinced myself it was true. That anything that I pick from the image, I can in fact hunt down a coset that maps there. Then the last piece, we have the one-to-one, and we can see that this is kind of condensed down. But everything besides this original little clearly part here is our one-to-one section. And let's see what's going on. So they set up a beta. Equal to a beta. Right, and again, that's how we set up one-to-one, right? Is that we pick out two arbitrary elements, and we say that their images are equal, and then hopefully conclude they must have been equal all along. Right, so I know that these two cosets, I want to say that they're the same at the end, if it's in fact one-to-one. All right, well, let's take a look at how we could show that. Let's get our guts in here. Well, the first thing they do is unpack, well, what does beta do? Well, beta is the map that takes us to the image of these representative elements. So far, so good. Oh man, they made some real quick jumps here. How did they get there? Let's let's unpack it. I know where I'm trying to head, but I want some more space because I think that they condensed things down and skipped a lot of steps, and I want to convince myself that it's true. All right, so the first thing it looks like they did is they tried to get the G1 and G2 next to each other. All right, well, I can do that too by going phi of G1, phi of G2, the inverse of that thing on both sides, which then I know gives me the identity. Because that would be inverse times the original thing on this side, and the inverse on that side. Cool. And I know because of some of my properties of how homomorphism works that I can pull that inverse inside. And because of how homomorphisms work, I am allowed to look at that product inside as well. So now, it took me a couple lines, but I'm seeing the same thing that they had in here. All right, and so what does that mean? It means that G of 1, G of 2 inverse equals E, and, the image of that equals E, and that is exactly our definition of kernel. So that's where they have the second claim here, that G1 inverse G2 is in the kernel of phi. All right, so then what is their next step here? Well, they look at this coset. They look at the coset G1 inverse G2 of K, and they note that this thing is in the kernel, or in K, right? That's what our K stands for here. And we talked about this before, I think, in some of those other proofs, that if you are just thinking of, like you're just picking other elements out that are inside your kernel, and you're operating by them, you're still just having your kernel. So that's what they're claiming here. It's like, since this thing is part of the kernel already, we operate on the left by it, we still just have the kernel set, which is great. I'm gonna draw one more little line down here. And then, what do they do to get to here? Well, it looks like they operate by G1 on both sides and arrive at G1K equals G2K. And that was our big goal, that if I picked two arbitrary cosets, because cosets are the things in my domain, and then I look at them and say, I'm going to assume they map to the same place, we can do a little bit of work and arrive at the fact that they must have been the same all along and were one-to-one. You can see part of why I'm writing all this out and demonstrating it this way is that a lot of the activity that we do in mathematics is really reading proofs that are out there. And reading proofs it's not like reading a book, right? Like, I'm not going to just hang out outside and leisurely read a proof like I would a novel. I read a proof with notes all over the place. I zoom out and think about the big structure. What are they trying to do? Where can I see those parts? And then I start thinking, well, how does this line imply that line? And you can see I drew a little picture to help me think about what was going on, and I had to unpack a lot of these lines to make sense of the implications. Like, why does this thing lead to that thing? And so as you're thinking about reading proofs in your future, I would highly recommend keeping some of these things in mind. That, one, if you're reading a proof and you don't understand it by just reading it straightforward, you are in good company with probably everybody who reads proofs. That there is a need to unpack lines, even when they do things like say, well, clearly. We still need to think about, well, why is this clearly? Can I make a little sub-argument to convince myself? And of course, they just kind of stopped, but let's actually wrap this up. Then beta is an isomorphism. And we can, in fact, conclude that G, kernel of phi, is isomorphic. That this set of cosets, this quotient group that I build, is exactly isomorphic to the image. All right, so I hope this is a useful exercise. I know there might be a couple points where you're like, I'm not exactly sure where that line worked. Feel free to kind of play around with those. If you have questions about a specific part, feel free to also reach out and talk to me about them. But the big thing I want you to walk away with is, what was the overall structure of this proof? How do we unpack little arguments involved? And how are we convincing ourselves? What is this beta? What is this phi? And now why can I say that this quotient group is exactly isomorphic to the image?